Hello, welcome to another session of Engineering Economics 2373. We are going to continue our discussion about the saving investment ratio. In this example, we have a project with multiple solutions for the internal rate of return, and we're going to see how we can use the saving investment ratio to avoid that problem. As we already computed in the previous video, we have here the present worth, or the present worth of each one of these cash flows. And in order to obtain the saving investment ratio, we add up all the negative cash flows together. And since we're interested in the absolute value, I am going to place a negative sign for all the negative cash flows to add, and the total is 22,446. Those are the negative cash flows, and then the positive cash flows discounted add up to 22,486. So the savings investment ratio is the positive divided by the negative, and the saving investment ratio we compute here at 10% is 1.001, is barely above 1, and therefore it is in the limit of accepting the project. We would accept it, but it's very marginal, the benefit. And as you can see, since we are dealing with just the present worth and the ratio of the present worth, we will not have the problems that we had with the internal rate of return. So again, the internal rate of return is the rate that allows us to compute or bring the present value of the project equal to 0. And how do we use this internal rate of return for the decision-making process? It's very simple. If we have a scale in which the minimum attractive rate of return is computed first, of course the minimum attractive rate of return should be larger than the rate of return that you would get in a project with no risk. A project with no risk, it would be the minimum that you would accept, because typically in any engineering project or any entrepreneurial activity will involve some kind of risk, and therefore the larger the risk, the larger the return you would expect. So the minimum attractive rate of return should be larger than the zero risk, and then above that you have the current projects to be selected should be larger, that should have an internal rate of return larger than the minimum attractive rate of return. Essentially the minimum attractive rate of return should be larger than the capital cost. And we're going to devote some time computing the capital cost later on. And for you to have in graphical form the formula that we use to compute the saving investment ratio. The saving investment ratio is the summation of all the cash flows, the positive cash flows brought back to the present, divided by the negative cash flows brought to the same period in time. There are other performance measures that we are interested in developing. One of them is the payback period, and the other is perpetuities. Let's see what they're all about. First, the payback period is the period that we will need in order to get back our initial investment, and essentially is the summation of the cash flows until they exceed the initial investment. This is the simplified formula, and this is a more proper formula because now we have taken into consideration the time value of money. Let's compute a couple of examples using this problem. Let's consider the following situation. We have a project which has 13 periods, starting with an initial investment of $1,000, and then the revenues are $150 for each one of the periods. The minimum attractive rate of return is 10% per period. So computing the cumulative cash flows, the positive cash flows that we have, we would add up 150 for the first year plus 150 in the second year. We would add up to 300 at the end of the second year, plus 150, 450 at the end of the third year, and so on and so forth until we get back our initial investment or better. And this would happen on the 7th period, in which with $1,050 we exceeded the initial investment of $1,000. A more complete representation would include the time value of money, in which if the minimum attractive rate of return is 10%, we discount each one of the cash flows by 10%, as we have seen in the past, and these present words for each one of these cash flows are added up together until we get the $1,000 back. So for the first year, the discounted value of $150 for the first year is $136.36. The present worth of the $150 of the second period, when brought back to t equals 0, is $123.97. Added those two together is that and the first year, it's $260.33. When we add the discounted value of $150 in the third year, which is $112.70, the total accumulated present worth cash flows is $373.03, and we have to keep doing that process until we get together $1,000, and that happens not in year 7 now, but until year 12, which is a more proper way to do it. So on year 12 we exceeded the $1,000 initial investment, and that would be our payback period. A special case of the computation of the payback period is when we have annuities for the same amount, and in such cases we can identify n by solving the equation for n when we have p given a expressed as it's in the formula we know. N would therefore be solved with the logarithm of a divided by a minus pi divided by logarithm of 1 plus I. Strictly speaking, we would need to round this up to the closest integer if it's not an integer. So this is what we call the ceiling of this function with 1 unit, and that's how we would obtain the corresponding result. In some cases, when we have projects that are presented to be sustained forever, what we can assume is that those annuities or the benefits that we're getting are going to be there for the rest of the life or until the foreseeable future, and then we assume that they are going to be perpetual annuities or simply perpetuities, and the way to compute the present worth of that is just by simply dividing these annuities by the internal rate of return, or by the minimum attractive rate of return rather, and we would use that as the estimation of the benefit of all those eternal benefits brought back to a single quantity in the present, and we can compare that to an initial investment, so to see if projects will be attractive under this situation. Let's consider an example for this situation. An initial investment of $1 million is required for a project, and the benefits that we expect is $150,000 for as long as we can foresee. If the minimum attractive rate of return that we can have for this project is 10%, then bringing back the quantities, all those eternal quantities, into the present will be equivalent to dividing 150,000 by 10%, and the total benefit, the cumulative benefit today, would be 1,500,000 if we subtract from the benefit of 1.5 million, we subtract the initial investment of 1 million. The total net benefit that we get is $500,000, and since this is a positive quantity, the decision would be that this is in fact an attractive project, and we will suggest it to be done.